Welcome to Lecture 10, Global Climate Models and the Future. Reading for this lecture is Chapter 4, pages 75 through 103. In this lecture, we will be discussing what global climate models are and how they can be used to determine future changes in climate. So we've been talking about the observations of global warming, and it would be helpful to understand whether the trends that we have seen over the last several decades will continue. And so, for example, will temperature keep going up? If so, how much? Will sea level continue to rise? How much will it rise? So global climate models can be used to help predict future changes in climate, as well as verify the causes of changes in past climate. So first of all, what is a global climate model? Well, it's a mathematical representation of the physical processes that control climate. And that's basically everything that affects climate, including the sun, source of all energy, the atmosphere, which is composed of greenhouse gases, aerosols, and other factors, the hydrosphere, the sphere of water, liquid water, the cryosphere, the sphere of ice, or the frozen sphere, if you will, the biosphere, the sphere of life, and the solid earth, also known as the geosphere. And the equations in a climate model are complex. Some of the world's largest supercomputers are running climate models. So the equations that determine how the atmosphere will change over time are very complicated. They're differential equations, and they have a lot of terms. And so in order to use those equations over the entire world, okay, we're talking about global climate models, you need really good computers, okay? So why do we need climate models? Well, we're already seeing the effects of global warming. 9 of the 10 warmest years during the instrumental record have occurred in the past 14 years. Okay, recall that. The warmest years since 1880, when the instrumental or modern meteorological record began, have occurred recently. September Arctic sea ice extent was about 50% lower in 2012 than in 1979. Remember that 2012 had the lowest September sea ice extent or area on record, going back to when the observations began in 1979. And it was about half of what it was in 1979. The 11 lowest September sea ice extents in the Arctic have all occurred in the past 11 years. And we've talked about how in the near future there will be ice-free summers in the Arctic. And that has a lot of consequences on the polar bear survival, on new shipping routes that could be used. Another effect of global warming is that sea level is going up. So in fact, global average sea level rose by 20 centimeters, nearly 8 inches, from 1900 to 2000. And that might not seem like a lot, but that's a global sea level rise. That's a global average sea level rise. Some parts of the ocean rise more, some less. So some spots of the ocean could rise perhaps a foot or two during the 20th century. And the sea level will keep rising. And so with global climate models, we will be able to determine how those changes will continue. How much will sea level go up in the 21st century? So climate models allow one to not only verify the causes of global warming. For example, as a preview of what we will be talking about, climate models cannot simulate observed changes in temperature from 1900 through present using only natural forcing factors. In order to simulate the observed changes in global temperature over the 20th century into the early part of the 21st century, the climate models need to include human-induced factors. They only include natural forcing factors, like volcanic eruptions, changes in sunlight. They can't simulate the warming over the 20th into the early part of the 21st century, especially the most recent warming in the last 4 decades, where that's been more dramatic. So they actually will help act as further evidence of the human connection on global warming. But they also will allow one to examine how climate will change in the coming decades, as we've been discussing. So, at this point, it would be helpful to look at a quick review of the observations of global warming and information on greenhouse gases that are responsible for the warming. So, here is a figure that we've seen before, showing the global average yearly temperature anomalies in black. Again, if the temperature anomalies are positive above the 0 degrees line here, then that year was warmer than the 1951 through 1980 average. And for individual years shown by the black tick marks that are lower than 0 Celsius, you see that happening in the early part of the 21st century more so, not as much in the later part of the 20th century, then the year was cooler. And you can clearly see how temperature rose over the 20th into the early part of the 21st century. And if you look closely, you'll see that the slope is greater in the last several decades. Of course, 2015 was the warmest year on record, in the modern meteorological record, that is. So how much will global temperature go up during the 21st century? We will be able to look at projections using global climate model simulations. Here's another figure that we've looked at, the famous Mann et al. Figure, published in 1999. This also shows temperature anomalies, but the data is a little different than on the last slide. This shows northern hemisphere temperature anomalies, and it doesn't just show the anomalies using the instrumental data from 1880 to now. It also uses proxy data in blue, data from the coral reefs, the ice cores, and historical records and tree rings, along with the instrumental data from thermometers shown in red. And this goes all the way from the Middle Ages in year 1000 to now. And it's sometimes called the hockey stick diagram. You see how temperature, there was actually overall a slight net decrease in temperature from year 1000 to close to 1900, and then you see the dramatic spike in temperatures during the last 100 plus years, 130 or so years. You can even note how the temperature started rising in the early 20th century, and then for a few decades it leveled off. It decreased some, and then in recent decades it's been spiking up again. We remember that the September Arctic sea ice extent or area is declining. We've seen this figure. And Arctic summers could be ice-free by 2040. So here's 2012, which had the lowest sea ice extent on record, going back to 1979, just over 3.5, about 3.6 million square kilometers. And the blue line shows the net trend, the net decrease over the period. Following the net trend, there would be ice-free summers in a few decades from now. But if you look closely, you'll see that since the mid-90s, about in the past 20 years, there's been a faster rate of decline of Arctic sea ice extent than in the earlier part of the period. So notice that from 1979 through about 96, 96 actually being the year at the highest September Arctic sea ice extent at 7.9 million square kilometers, there wasn't a whole lot of change overall. Yes, the value, the measurements go up and down from year to year, but the net trend was pretty flat. And then look at how, from in the last 20 years, the rate of decrease, the slope, it's been steeper. It's the Arctic sea ice is declining faster in September than the net trend over the period. So that's why we think perhaps sooner than in 3-4 decades, perhaps the summers could be ice-free, or at least very close to ice-free. Sea level is going up, and there's a couple causes for sea level rise. Not so much the melting of the Arctic sea ice, but melting of continental ice along with thermal expansion. So we've talked about the cryosphere, the component of all ice, the Earth's sphere of ice, and it includes the ice sheets of Antarctica, Greenland, Patagonia. It includes snow fields, sea ice, glaciers. But most of the sea level rise is due to melting of continental ice, especially the melting of the continental ice along the edges of the ice sheets of Antarctica and Greenland. Patagonia is pretty small. And so what happens is the ice melts on the edges of Antarctica and Greenland, turns into fresh water. From ice, it turns into liquid water, and it flows into the ocean, and it causes sea level to go up. Also, as the surface warms, not only do the surface air temperatures go up, okay, the ground is warming and the air in contact with it in the lower part of the atmosphere is warming, but the oceans are warming as well. And as the ocean warms, the water expands. We've talked about how as air, for example, warms, it expands. It's true for any substance. So as the oceans warm, they expand, and so they vertically rise, okay? And so when you look at how sea level has changed over the 20th century, you see that at the beginning of the period, the sea level changed, the departure was close to zero, and now, as of now being about 2000, sea level is about 20 centimeters or 7.87 inches higher in 2000 than 1900. And by the way, just recently in the past 16 years since 2000, sea levels have gone up a few more inches. In fact, it's just in the last couple of decades, sea level is really starting to rise at a faster rate. So how much is sea level going to go up during the 21st century? Well, a few years ago, the consensus was a 2 to 4 foot rise. Okay, about 2 to 4 feet. And think about that. In between 1900 and 2000, sea level went up less than a foot. Went up about 2/3 of a foot. And in the same time period, 100 years, in the 21st century, sea level is going to go up 2 to 4 feet. But times have changed. Especially off Antarctica, the West Antarctic ice sheet is melting faster than the climate models are projecting. And there's evidence that sea level is rising faster than the climate models were projecting. And so now there seems to be a consensus that we are locked into at least 3 feet of sea level rise over the 21st century. And the range has been changed from 2 to 4 feet to 3 to 6 feet. Okay, we'll talk about the effects of this. Not everywhere sea level is going to go up 3 feet. Some places it could go up more. And for like a state like Florida, which is the majority of the state is right at near sea level. Okay, there's major consequences for low-lying coastal areas like San Francisco, San Jose, Venice, New York, New Orleans. There's major impacts in the coming decades from sea level rise. So, now we will look at the observations and touching on what will happen in the future. And we'll get into more detail. We'll look at more specific values, look at some diagrams of climate model projections. But now let's understand what is driving the changes in climate. And by the way, when we look at global climate models, we would ask, we have more proof of the drivers of climate change? So we understand that the planet's warming is mainly driven by changes in greenhouse gases, increases in greenhouse gases, an enhancement of the greenhouse effect. So let's review the greenhouse gases responsible, the names, contributions, sources of them. So here's a figure showing concentrations of the three most abundant anthropogenic greenhouse gases: carbon dioxide, CO2, methane, CH4, and nitrous oxide, N2O, from year 0 to 2005. And carbon dioxide and nitrous oxide concentrations use the y-axis, the vertical axis on the left, with the carbon dioxide concentrations in parts per million, the nitrous oxide concentrations in parts per billion, and the methane concentrations are shown using the right vertical axis in parts per billion. So for most of the what would you call this? The second millennium since zero, right? There was the or what would you call this? The first two millenniums since zero, right? 0 to 1000, and then 1000 to 2000. For most of that 2000 year period, okay, there wasn't a whole lot of change in CO2, CH4, and methane, and N2O concentrations, okay? CO2 concentrations are pretty consistent at about near 280 parts per million, right? All the way from 0 into 1700, okay, even into 1800, around the beginning of the first industrial revolution. Methane concentrations slowly began increasing from around a little over 600 parts per billion, 650 parts per billion, which is 0.65 parts per million, to 700 parts per billion. Not much change, right? And nitrous oxide concentrations went from around 260 to 265 parts per billion to 270 parts per billion. Not a whole lot of change. But that's until we got to about 1800. Then what happened in that 205-year period from 1880 to 2005? The concentrations began rapidly increasing, something that hadn't been seen for going back 1800 years, and by the way, back further in time as well. Okay. Recall, for example, if you look at the carbon dioxide concentrations, the CO2 concentrations were never above 300 parts per million, going back 800,000 years before the early 1900s. And if you look back, going back that long, and you see that dramatic spike just recently. And so CO2 concentrations have, of course, increased to now over 400 parts per million. Methane concentrations, shown in blue, are now near 200 parts per billion, 2,000 parts per billion, or 2 parts per million. So methane concentrations have increased as well, and so have nitrous oxide concentrations. Nitrous oxide concentrations are now exceeding 300 parts per billion. They're getting close to 350 parts per billion. So we can look at a table we've seen before showing the properties of the major anthropogenic greenhouse gases, a figure from your book. Now this is 2010, or that's when the book was published. So some of these concentrations have changed just in a matter of 6 years. Of course, we know that carbon dioxide concentration is now over 400 parts per million, or 400,000 parts per billion. Methane concentrations are near 2,000 parts per billion, or 2 parts per million, and nitrous oxide concentrations are approaching 350 parts per billion, or 0.35 parts per million. And we talked about the radiative forcing diagram. We understand that carbon dioxide has the largest radiative forcing term, or the largest magnitude of any radiative forcing term. And so it lasts in the atmosphere 120 years. And even though, say, methane for example, has 25 times the warming potential. A single molecule of methane is 25 times as strong a greenhouse gas as a single molecule of carbon dioxide. Well, there's about over 200 times as much carbon dioxide in the atmosphere as methane. And carbon dioxide lasts 10 times as long on average in the atmosphere than methane. So overall, the effect of carbon dioxide is much greater than methane. Nitrous oxide, you see, lasts almost about as long as carbon dioxide in the atmosphere. And the warming potential is nearly 300 times as great, but thankfully it exists in concentrations of less than 1,000th of CO2. Okay. So, let's review these greenhouse gases. Let's review some of the sources of them, where they come from. Let's try to answer the question: how much of the global warming we've seen is caused by a single greenhouse gas? Okay, there's statistics offered in the book that we'll be discussing. So carbon dioxide, CO2, we know it's the most important anthropogenic greenhouse gas, or AGHD, in terms of concentration and total effect, shown by the radiative forcing diagram. Now, if we wanted to ask what percentage of global warming, that is, we know global warming is primarily human-induced, is due to CO2, it's about a third. Okay, so 33%, a third of the global warming is just due to one greenhouse gas alone, carbon dioxide. And CO2 emissions from fossil fuel burning, the primary source or the primary way to put CO2 into the atmosphere from humans, went up by 58% from 1980 to 2006. From 20,000 million metric tons per year in 1980 to over 30,000 million metric tons per year in globally in 2006. Okay. So where does carbon dioxide come from? Largest source generally in the world and in the U.S. is power generation. Second largest is transportation. Third largest is industry. Okay, and there's others too: agriculture, home and commercial energy usage. So fossil fuel burning, of course, includes the burning of coal for power, natural gas for power and for heating and transportation, burning of oil for transportation, for manufacturing. So I like to show this figure you've seen before because it's just so powerful to see the dramatic rise in carbon dioxide emissions from 1850 to basically present. Carbon dioxide emissions for the world slowly increased from 1850 as we got into the 1950, and then you see how in the last 6-7 decades, the second half of the 20th century into the early part of the 21st century, the dramatic rise, okay, from 1950 to basically now, global CO2 emissions have increased by a factor of 7, okay, 7. And by the way, what we like to understand is, what do we have to do to carbon dioxide emissions to start to mitigate against global warming? The trend has been this increase, okay, overall. And climate models will actually allow us to determine how global CO2 emissions have to change in order to stabilize CO2 concentrations. So we've talked about how in 2100, global carbon dioxide concentrations will be anywhere from 550 to about 970 parts per million. So you might be wondering, well, in the best case scenario, let's say we level off CO2 concentrations at 550 parts per million, what do we have to do to emissions? Can we keep increasing them? Do we stop increasing them and level them off? Or do we have to decrease them? And if so, how much? Okay. And you start to see at the very end of this historical data this little tick where for a year or two there wasn't much change. And by the way, after that, going to the early 2010s, CO2 emissions were increasing again. But there was a possible stall in 2015. There's evidence that from 2014 to 2015, global CO2 emissions did not increase, even though the economic growth continued. And there's evidence that perhaps in 2016 there will be a decrease. Okay, 2016 is only a little over halfway through, so it will be a while before we have the total 2016 global emissions. But is this a sign of things to come? There's been a lot of efforts by governments, influenced by scientists, to reduce emissions, and so we might be coming to a time. It could be a temporary bump in the normal increase in emissions, but there could be a time. It could be the stall in emission growth could be a clue of a change, where perhaps for a few years the emissions will remain pretty constant, and then they will start decreasing. So the second most abundant anthropogenic greenhouse gas is methane, or CH4. And it is the culprit for about 15% of global warming. Okay? So you notice that if you add up the contributions to global warming from carbon dioxide and methane, you get about 48%, nearly half of all the global warmings, just due to those two greenhouse gases alone, signifying how important they are. Okay? Where do methane emissions come from? Well, most of the world's rice is grown by flooding of paddies, okay? A lot of people eat rice in the world, and to grow it, you generally flood these paddies, and when that's done, that can actually lead to microbes in the water emitting methane, okay? So that's a prime principle, a great source of methane emissions. Now, methane emissions can also result from livestock, okay, cows moo, sheep baa, goats scream, right? And so you see these agricultural sources of methane, both from growing of rice and from livestock on farms. Now, natural gas, which you've been discussing in regards to the Green Ninja Project, it's used at home to for heating, space heating, water heating, cooking heating, okay? And, by the way, you might be wondering, well, you might be a little puzzled, or you maybe not, but you might be wondering, well, we've been talking about how PG&E tracks your daily electricity and natural gas usage at home. And you might be saying, well, actually, California's largest source of electricity generation is natural gas, right? How are they different? Isn't natural gas used to make electricity? Well, it certainly is. But electricity directly, it's not the same as natural gas. It's made from natural gas, okay? But it's not the same. You don't have natural gas running, for example, through your electric lines. You have electricity. So the natural gas is actually in that form itself, okay? And so that can be, again, used for water heating, space heating. And so if there's an electricity leak, you're not in the electric wires, you're not going to have natural gas coming out, even though electricity is made from natural gas. But if there's a natural gas leak, that's an issue, okay? So I just wanted to clarify that. Now, it can be released in many ways. When we obtain natural gas. Okay, so when we extract natural gas from underground, okay, fracking, process the natural gas, okay, distill it, you get out the unwanted substances, purify it, whatever is done, store it. Well, when it's extracted, it can leak out, okay, of the earth. When it's processed, it can leak out. and released to the atmosphere, the natural gases, which is mainly made up of methane. So think about it, if the natural gas leaks, well, methane also is released or leaks, because natural gas is mostly methane, about 70-90%. When natural gas is stored, methane can be released, and finally, when natural gas is transported via pipeline, methane can be released, okay? And then, of course, when you burn the natural gas in a power plant to generate electricity, that can release methane to the atmosphere. All right. Now, ozone, or O3. Of course, we know it's very important in the stratosphere. That's where most of the ozone is. Almost all the ozone in the atmosphere is. It protects the humans from ultraviolet radiation from the sun. We talked about the ozone layer. But actually, it does operate as a greenhouse gas in the troposphere, okay, lowest layer of the atmosphere, and it's accountable for about 13% of global warming. And actually, ozone has a greater contribution to global warming than nitrous oxide, so that's why it's listed here ahead of nitrous oxide. Where does it come from? It originates from smog, generated by reactions of carbon monoxide and nitrogen oxides. So when carbon monoxide and nitrogen oxide react, they can generate smog. And the ozone comes from the smog. Carbon monoxide is an odorless, tasteless gas. We know about if concentrations rise in the home, that can have damaging effects. So it's very important to monitor carbon monoxide levels in your home. Nitrogen oxides, NOx, basically chemicals that have one nitrogen atom and one or more oxygen atoms, different from nitrous oxide, N2O, which has two nitrogen atoms and only one nitrogen atom, only one oxygen atom. Now, where do these chemicals come from? Different sources, including, this isn't in the order, but the three largest sources of CO2, by the way. Transportation emissions can release carbon monoxide and nitrogen oxides. Okay, we talked about how your car emits carbon monoxide. That's why it's important not to, stay in your garage with the car on, with the carbon monoxide emissions coming out of the tailpipe with the garage door closed too long. Power generation, coal power plants emit carbon monoxide and nitrogen oxides, and so do manufacturing plants or factories, right? Tropospheric concentrations have increased, okay? So now, if you look at these three greenhouse gases, carbon dioxide, methane, and ozone, you'll see that those three are responsible for 61% of global warming. Finally, let's take a look at nitrous oxide, N2O. About 6% of global warming is due to N2O. Okay, not a whole lot, but it's still responsible for a fraction. And if you add up the contributions of these four greenhouse gases, carbon dioxide, methane, ozone, nitrous oxide, you see that those four can explain 2/3 of global warming. Okay, 2/3 of global warming. Right, 67%. And carbon dioxide is responsible for half of that 67%. It's responsible for as much of global warming as methane, nitrous oxide, and ozone combined. Okay, so then you might be wondering about, well, what about the other third? Okay, that's still a third, right? That's a significant portion. What does that due to? Well, it's due to smaller greenhouse gases. These four greenhouse gases have the largest contributions to global warming. Okay, no other greenhouse gas has more than, say, a 6% contribution. So, but if you add up, like the smaller ones, sulfur hexafluoride, carbon monoxide, they might be small percentages, but they add up.
And then there is a fraction due to, for example, solar irradiance. The sun has become a little stronger, and that has a small contribution to global warming. There are more aircraft contrails now, and that has a small contribution to the warming of climate. Okay, so there are other factors too. Not 100% of global warming is human induced, but the large majority of it is due to increases in these anthropogenic greenhouse gases. And nitrous oxide is primarily emitted from agricultural activities, but different ways than in methane. So while methane can come from the livestock and the flooding of the rice paddies, nitrous oxide generally comes from irrigation, watering, fertilization, and pesticide use on crops. Okay. Nitrous oxide is also known as laughing gas. It may be used to help quote unquote relax you during a dental procedure. Okay, let's come back to global climate models. Talk about the core concepts of them. Okay, so these are three important concepts to understand for global climate models. One, they separate Earth into at least two sections, the atmosphere and the ocean. So the most basic global climate model, or GCM, that stands for global climate model, is going to have at least two different sections for Earth. An atmosphere, where like the aerosols, the clouds, the greenhouse gases are, and the ocean, where most of the world's liquid water is. Then, each section, the atmosphere and the ocean, is broken into submodels. Okay? So depending on, and the more complex, the more detailed the model, perhaps the more subsections or submodels. Okay, so you can break the atmosphere into gases, into aerosols, into precipitation, into clouds, right? You can break the ocean into composition, currents. Okay. And the thing about it is that the GCMs break up Earth into grid boxes, each of which obey the laws of physics. So global climate models are models. They don't resolve every single point of Earth, right? Think about what a model is, okay? It's basically a simplification it's a representation of an object or of some system, if you will, that makes simplifications. Okay, so it's not as detailed as the real thing. So a model car. If you're a kid and you collected model cars, you built model cars. From farther away, it looks real, right? And then you go closer in. And examine it at a shorter distance, and you see there's simplifications made. Okay, it's not as detailed as the real thing. Similar with global climate models. Instead of resolving every single point on Earth's surface, which would require way too many calculations and would take too long, it would take much longer to actually see the results of the climate model. It would take longer than it actually happening, so they wouldn't be useful. What's done is to resolve the Earth into these grid boxes, which are three-dimensional. And each grid box will have a certain value for a different meteorological variable. So each grid box will have a temperature, a cloud cover, a wind speed, a wind direction, a humidity, relative humidity, and so on. More about these grid boxes. The model accuracy improves as the grid boxes become smaller and the time step decreases. So as the grid boxes become smaller, the resolution increases, right? And as the time step between projections decreases, the model becomes more accurate. You might be wondering, what is this time step? Basically, when the model runs and then it creates an output of future climate, it doesn't just put out a forecast for one certain year. It runs and it puts out projections
for different times, and the times are separated by a time step. Okay, so maybe it puts out projections for every year, so the time step would be a year. 2017 temperatures, right? 2018, 2019, 2020. And the global climate model, as we'll begin to look at when we look at the figures showing projections, they don't just look at the temperature for the whole globe, but they'll look at temperatures for different parts of the globe. So they're global in the sense that they actually resolve the Earth into these grid boxes, okay, over the entire globe. And their grid boxes are three-dimensional, so they're not just at one level in the atmosphere or near the surface. They run throughout the atmosphere. So the time step decreases and the model accuracy improves. And the thing is, this increases running time. As the grid boxes become smaller, okay, the model has to, it takes longer to run because it requires more computations, more calculations, okay? And as the time step decreases, the temporal resolution improves. So when the grid boxes become smaller, the horizontal and or vertical resolution improves. The length, okay, width and height resolution can improve, become better. And as the time step decreases, the temporal resolution improves. But this causes more calculations, and so the running time becomes faster. Now, over time, model resolution has increased. Today's climate models are higher resolution than the earliest climate models. Okay. And you might be wondering why. I can ask you, why do you think model resolution has increased? Well, computers have become faster and more powerful. Computers are more powerful. They can now, they have more space. They have more available space, and they can do more calculations, and they're faster now. So now you can do more calculations in a shortened time period, and so the resolution has gotten better. Example, the United Kingdom Meteorological Office Global Climate Models, in 1959, the early years of their climate models, the climate model could do 3,000 calculations per second. 3,000 total calculations per second, and it had two vertical levels representing the atmosphere. Okay. Yes, 3,000 calculations sounds like a fair amount. But compare that to 2004. 45 years later, their global climate models could do 20 trillion calculations per second. So that's an increase from 3,000 calculations per second to 20 trillion calculations each second. Right, and so that's 20 trillion times 60, 1,200 trillion calculations a minute. And in 2004, the climate models had dozens of vertical levels. So you see how the computers became faster, and the resolution increased, more levels vertically, and also, I'll tell you, more horizontal resolution, better horizontal resolution. Okay. So, you think, well, how can that be done? How can you have 20 trillion calculations a second? That comes to back what we were talking about earlier. Some of the world's largest supercomputers are running climate models. So here's an example of that. Here's a figure from the book, figure 4.6, showing the main floor of the Earth Simulator Center in Yokohama, Japan. And this is these are basically processor nodes. These are parts of the supercomputer, if you will. The Earth Simulator Center, it's a global climate model in Yokohama, Japan, has 160 processor nodes. And so these are parts of the supercomputer, okay? These supercomputers are extremely large. They're the size of rooms, even floors, okay? This is just the main floor of the Earth Simulator Center there in Japan.
And kind of interesting, really interesting what these look like. If you look at them closely, what do these look like to you? Especially focus on the endings here, okay, facing you, and these tops of these structures. They kind of look like the Bart fair gates a little bit, right? That's kind of what they look like, which is interesting. Anyway, here are the elements of a global climate model. We're talking about the global climate model has to have at least 2 sections, atmosphere and ocean, but each section can be further divided into submodels. Okay. So, here's a figure from the book showing elements of a global climate model. There's separate models characterizing processes in the atmosphere, shown here in bold, the oceans in bold, land, and sea ice. So if you first take a look at the atmosphere, you see there's aerosols, there's microscopic solid liquid particles suspended in the atmosphere. We were talking about the different examples of them in Lecture 8. Chemistry of the atmosphere, okay, the different chemicals in it, the makeup of them, relative concentrations, right? Clouds, which can reflect sunlight, contribute to the albedo effect. They can absorb and emit infrared radiation, contribute to the greenhouse effect. For land, there's different components of land. There's snow cover, very high albedo it has. There's vegetation, which can absorb carbon dioxide through photosynthesis and release it during respiration. We talked about albedo. Topography affects climate. Can affect the wind. Mountains can deflect the winds. Mountains can produce precipitation. Okay, when air rises on one side of the mountain, it can be forced to produce precipitation. And so you see how the different parts of a climate model have the different major sections of a climate model, at least the atmosphere and ocean. Okay, those are the 2 sections at the minimum a climate model has, but it can also have land. Okay, there's different components of each. Oceans, there's currents. Okay, the California current runs along the west coast of the U.S., and that's why we don't get hurricanes in California, because it's a cold current coming from the Gulf of Alaska. Hurricanes need warm ocean water to survive. Ocean temperatures are warming. The oceans, of course, are made of salt water, not fresh water. So, and the different parts of the ocean have different salinities. Okay, so hopefully you're getting an understanding of all these different processes that are found inside a global climate model. Now, how old are global climate models? Let's look at a brief history of them. And you're not going to need to know all these different acronyms, all these different abbreviations, but this is just given to show you when the climate models began, how they evolved, different agencies that have climate models. Okay, so the black arrow means a direct line of development. Okay, so one climate model was developed directly from another. White arrow means one climate model had a major influence on the formation of another. And the bar means just a bar with a dash or a tick at the end means development stopped. Okay, so question: when did the first climate models begin? When? Well, late 40s, the Phillips GCRS model. Okay, so here's 1960. Here's 1955. So the early 50s. Sorry, I said late 40s. Scratch that. Early 50s. Okay. There is the Lawrence Livermore National Lab climate model that began around 1955. UCLA climate model began in the late 50s. Okay, so in the 50s are when the climate models began. And
of these atmospheric global climate models, you see how the UCLA one had a lot of influence on other climate models beginning. So, for example, the RAND climate model began after being influenced by the UCLA one. UCLA version 1 model. The UCLA version 2 global climate model had a major influence on the development of NASA's global climate models. Okay, so and you see different agencies that have climate models. The Navy has climate models. Lawrence Livermore National Laboratory does. National Center of Atmospheric Research in Boulder, Colorado has climate models. So hopefully you're getting an understanding and recognize that as we went forward through decades, through the 60s, 70s, and 80s, the climate models became faster, their resolution increased, they became better able to provide a complete picture of for the Earth's climate. Now, talking more about grid boxes, here are some examples of grid box systems. On A is basically the Earth not showing the continents or oceans and not looking at any values, but just showing the grid boxes, specifically the centers of them. So what's being shown is how Earth is resolved into them. And this is just looking at from above. And so you see basically the dot at the center of it. So the dot will be at the center of the grid box. And the grid box will have the same value for temperature, wind speed, wind direction. And B actually overlays the continents and now an actual variable, temperature. So the colors represent temperature, as you might surmise. The orange and reds represent hotter temperatures, okay, over the tropics, and then as you go further north in the mid-latitudes and again the poles, you start to get into the greens, followed by the blues, and then the purples, colder temperatures. And notice how each temperature, the temperature of each grid box, okay, each grid box has one temperature, okay, one color, and that's what we're talking about. Each grid box has the same temperature. And by the way, another thing that needs to be mentioned is these are just sea surface temperatures. So you see the continents basically have the same color. And then if you're over the oceans, Pacific Ocean, Atlantic Ocean, Arctic Ocean, you see the varying colors. You're just looking at the temperatures of the oceans, okay? So global climate models characterize fluxes into and out of a grid box during a time step. These grid boxes are three-dimensional, okay? There's many of them throughout the atmosphere. And they exchange energy and matter with each other. So they're not closed off from one another, okay? Energy, heat, moisture, it's allowed to be exchanged between them. And that's important because that's what happens in the real atmosphere. That's what happens in the oceans. That's what happens in the Earth. You know, material doesn't just stay in its own compartment or box and just not move around, okay? There's constant interchanging of material, okay? So this is important. Now, what goes into a climate model and what comes out of a climate model, okay? You might be wondering. So what do we have to put into the climate model in order for it to run? And then after it does its computations and it does its run, what comes out? Ideas? Well, the input of a climate model includes a lot of different variable factors, but a couple examples of the input are changes in atmospheric greenhouse gas concentrations. Okay? How the atmospheric greenhouse gas concentrations have changed over time. Changes in albedo due to aerosols. Okay? How the more aerosols has led to a change in albedo. Okay? What about output of a climate model? What do you think comes out of it? Well, basically future climate, such as how temperature will change, okay? How precipitation will change, how sea level will change. And global climate models don't just show how the entire world will warm up. We talked about how from 1900 to 2000, from 1915 to 2015, global Average temperature went up 0.97 Celsius or 1.75 degrees Fahrenheit. The global climate model is not just going to say, oh, from 2000 to 2100, the world's temperature will go up by this amount. It's going to allow you to see how temperature increase varies over the world. How, for example, how much is temperature going to go up in the Bay Area? How much would temperature go up on average in the Arctic? How much would temperature go up on average at the equator? Okay, and this is really useful because people want to know about how the climate change, global warming, that form of climate change will impact their lives specifically, right? So if you just say, oh, global temperature is going to go up this certain amount, it might not mean a whole lot to the average person, right? It might mean a lot to climate scientists. But if you can start to say, well, how much hotter is San Jose going to be, right? How are this and ask questions like, and answer questions, are the heat waves going to become more common, right? What are the record high temperatures of San Jose going to be like in 2100? Is San Jose going to become drier? Okay. How much is sea level going to go up near San Jose? And then, therefore, what parts of San Jose will be underwater? Okay. So, now, talking about emission scenarios. It is unknown exactly how greenhouse gas emissions will change in the future, right? And because of this, scenarios are developed. Okay? So an example of how we don't know exactly how the emissions will change in the future. There was a stall in global emission growth in 2015. Okay? Now, is this a turning point toward reducing emissions in the coming years where we see global greenhouse gas emissions decrease, a dramatic change from what's been happening for tens of years, even hundreds of years? Or is this just a temporary bump in the road of emissions continuing to increase, right? Maybe the emissions level off for a year or 2 or 3, and then emissions keep going up. So we are not sure. So we need to develop emission scenarios for the climate models that look at different possible paths of emissions. Okay, will emissions keep going up? How much? Will emissions stabilize? Will emissions decrease? So global climate models take into account different emission scenarios and then forecast climate change based on them. Okay, so there's actually a range in the projections of temperature increase, sea level rise, okay, hurricane intensity based on emission scenarios, okay, because we're not sure exactly how emission scenarios will change. We hope we reduce emissions, we hope for the best, but we have to prepare for the worst, right? So what factors can affect greenhouse gas emissions, right? So that's a question I have for you. Can you start to think of some different factors that determine what emissions will be like in the future? What could cause greenhouse gas emissions to change in the future? What could cause them to vary, or what could cause them? What could cause differences in the changes in emissions in the coming decades? Think. So here's a list of some factors. Global population. Okay. Why? Well, the more people on Earth, okay, that alone, then generally the higher the emissions, okay? Now that's not net, it doesn't have to be. That's been the case. As global population has increased, emissions have went up, okay? Because the more people on Earth, the more electricity you need in homes, the more products you need made for people's lives, the more cars you have, right, on the road, the more flights in the air, as you have more people and there's more traveling, right? So what is the global world's population right now? It's at over 7 billion. It's about 7.3 billion. Okay, different depending on what world population clock site you use. Okay. What's the population of Pokemon characters in the Pokemon Go game, by the way? Okay. Now, it's projected to increase. How much? Well, by mid-21st century, in 2050, in a few decades from now, the world's population will be between 10 and 13 billion. Very good probability of that, okay? And it's a range, okay? It could go up to 10 billion, which is, if the world population goes up from just over, slightly over 7 billion, let's say 7.3 billion, to 10 billion by 2050. Well, that's about a 37% increase. But if the world population goes up to 13 billion by 2050, then you're talking about nearly a doubling in population. Okay, and that when you'd expect a lot more emissions. Okay. So that's one. Here's another. Energy generation. We've talked about in Lecture 9, energy and emissions, how for decades energy generation in the U.S. has mainly relied on the burning of fossil fuels. So do we continue to be fossil fuel intensive for U.S. and the world? Okay, we're talking about global emissions here because we're dealing with global climate models. Or do we switch to renewable sources? Does the world switch to methods of generating energy that are clean, they don't have emissions, or they don't have as high of emissions as fossil fuels? Okay, and this is also good because, again, we only have a finite supply of fossil fuels, so we will be forced to change our ways to generate energy in the future when we run out of the fossil fuels. Okay. Here's another factor affecting emissions: economic growth. In general, during the especially later part of the 20th century into the early 21st century, as the economies of countries grew, their emissions grew. Okay, because their economic development was tied to things like making more products. Okay, more products manufactured for certain countries. Okay, not all. Economic growth could be related to population increase. Okay, it could be related to more oil. Okay, and so one factor we need to look at is type of economy. Is it material based? Okay, is it based on making products, or is it science and technology based? Because there's been examples in recent years that the economy can grow, but without necessarily increasing emissions. So, for example, from 2014 to 2015, overall, the world global economy grew. Globally, the economic value of the world increased, but the emissions didn't increase. Okay, so can the economy be more science and technology based? Can the economy be more based on renewable energy sources, ways of making renewable energy? Okay. Here's another one. Cooperation among countries. Is there a more homogeneous world where countries share technologies, share information with one another, and so perhaps the poorer countries that don't have access yet to the information, the science, the technology of the more developed countries, or perhaps the richer countries, can they learn? Can information be shared, and then they learn, and they can learn ways to reduce emissions? Okay, they can be exposed to renewable energy sources. They can be exposed to important medical information. Okay. Or do we live in a more isolated or heterogeneous world where there's a greater separation between the rich and the poor nations? So, these are some factors affecting emissions. So when we talk about emission scenarios for climate models, it turns out that there are 4 major storyline scenarios.
A1, A2, B1, B2. Okay? Right now, that doesn't mean a whole lot to you, okay? There's just letters and numbers, but we'll go into them. What the 4 storyline scenarios represent, how they differ. And they differ in their emission scenarios, and we'll talk about how so. Okay? So first of all, it turns out that A is a category, and B is a category, and 1 is kind of a category, and 2 is a category. So let's talk about that. We have high emission scenarios and low emission scenarios. So both A1 and A2, both of those storyline scenarios, are considered high emission scenarios. They assume a world of rapid economic growth. Okay, so the economy of the world grows at a fast rate, and rapid introductions of new and more efficient technologies. Okay, and this is something we've seen. Technology's improved. We're seeing all these new technologies in recent years. It's becoming more efficient. Okay. So A1 and A2 both are examples of this high emission scenarios, but they differ exactly. They differ. We'll talk about how so. And B scenarios, B1 and B2, are low emission scenarios. They assume a world of dematerialization. In other words, the economy is not so material based anymore. The world is less material based as a whole. And the B scenarios take into account introduction of clean technologies, renewable technologies. So, the A scenarios are more economic, more geared toward economic growth, but the B scenarios are more environmental. Okay? Now also, the number 1 means something. Just like the letter A and B, the letters A and B mean something, the numbers mean something. A1 and AB1 are more global, more homogeneous scenarios. Okay, so there's more sharing between the countries of the world. Whereas A2 and B2 are more regional, more heterogeneous. There's less sharing of information, technology, science between the countries of the world. Okay, and then you'll see here A1 has 3 basically categories or sub-scenarios. B, balanced. FI, fossil intensive. T, non-fossil, technology based. And again, we'll be looking at these 4 storyline scenarios in detail. But first of all, let's look at how the emissions from each vary in the coming decades. Okay. So one thing you might be expecting is that A1 and A2 will have higher emissions. Okay. And B1 and B2 will have lower emissions. So here are the 4 emission scenarios, and here are carbon emissions in gigatons of carbon per year from year 2000 to 2100. And A1, as you know, has 3 kind of different sub-scenarios, A1FI, A1B, and A1T. Now the red line indicates the predictions for one basically certain scenario within the one particular run of the scenario. It turns out that even for each scenario, each of the 4 storyline scenarios, there's a range in emission scenarios. Okay? In a single emission scenario itself, A1, A2, B1, B2, there's different runs, okay? So they vary the conditions slightly. So the shading for each represents the total possible range in emissions for a given year, and red is just kind of one run, if you will. Okay. So let's take a look. And by the way, we're looking at carbon emissions in gigatons of carbon per year. To convert to carbon dioxide emissions, basically multiply the gigatons of carbon per year by 3.67. So, for example, you see that as of now, actually all the scenarios, the gigatons of carbon per year emitted in the world, it's about 10. That translates to around 36.7 gigatons of carbon dioxide per year, and that's about what we're at. We're at about that now for the world. Okay. Now, what happens when we go future? I ask you for A1FI, what happens to emissions, global carbon dioxide emissions, as we go forward? What happens? It increases. They increase, I should say. Okay. So they're at 10 gigatons of carbon per year now. By 2040 or so, the world is emitting around 20 gigatons of carbon per year. And they continue to increase. The rate of increase decreases, but by 2070, 2080, the world is putting in 30 gigatons of carbon per year. That's 3 times as much now. So imagine what if the world is putting 3 times as much carbon dioxide into the atmosphere than as now. Imagine how carbon dioxide concentrations are going to go up. Okay, we'll see that too, how the concentrations change. A1FI is fossil intensive. We'll tell you now, this is business as usual. This is actually the worst case scenario. There's 4 storyline scenarios, but if you take into the fact A1 has 3 groups, there's really 6 total scenarios. And A1FI is the worst case scenario in terms of global warming. It has the highest temperature increase, the highest sea level rise, okay, the highest CO2 emissions and concentrations. A1B is a balance between heavily relying on fossil fuels to generate energy, and technology helping us improve our ability to generate energy using less fossil fuels, okay, generating more energy, let's say, by burning the same amount of coal, oil, natural gas. And for A1B, you notice emissions, yes, continue to increase until the middle part of the 21st century, and then they slowly start to decline. Okay, so that's good. And for A1T, it's even better. Emissions slowly increase, not nearly as much as A1B or A1FI, and then they start to decrease. Okay, by the end of the century, the world's emitting less carbon dioxide than now. Okay, technology really helps us. For A2, emissions keep going up. Okay, they don't stop and then level off or start to decrease. Okay. But even though they level off, they don't get quite as high as A1FI by the end of the 21st century. B1 has emissions slowly increasing, not by much, just a little bit by the middle part of the 21st century, and then leveling off. Okay, a significant decrease for decades. B2, slow increase, but still relatively low emissions by 2100. Okay, let's talk about the scenarios in detail. A1 assumes a world of rapid economic growth. It also assumes population peaks in 2050 at 10 to 13 billion. Okay, and then it decreases afterward. And we didn't cover this specifically, but you might be wondering, what are the factors that directly affect population of the world? Well, what do you think? Birth control laws, okay, like, some countries have the one-child law. Access to medical care. Access to pharmaceutical drugs, right? Because that can affect life expectancy. That can affect how many people survive, right? Disease, okay, war, right? Lots of factors. Different branches are dependent on energy type and use. So A1FI is fossil fuel intensive. Business as usual. We continue to depend on coal, oil, and natural gas to generate energy. A1T is non-fossil fuel intensive energy use. Technology really helps us get away from relying on fossil fuels. And A1B has a balance between fossil fuel and technology for energy generation. A2 storyline is a heterogeneous world. So the technologies are not shared across borders. The countries are more isolated from one another. And the population continues to rise throughout the 21st century. It doesn't just peak in 2050 and then level off. B1 storyline has a similar population as A1. And global exchange and cooperation between countries, a homogeneous world, as does A1. But unlike A1, which assumes a world of rapid economic growth, and it's a high emission scenario, B1 has a focus on social and economic sustainability, okay, and ways to have an economy that's sustainable. And it really looks at renewable energy sources, okay. B2 storyline has a population like A2. It's also environmentally and socially focused like B1, but unlike B1, which has a more homogeneous world, B2 has a more heterogeneous world. Now, we talked about A1 FI is kind of the worst case scenario. B1 is the best case scenario. Okay. So let's start looking at what CO2 concentrations will be like in 2100 based on the different emission scenarios. Here we go. We have observations of CO2 concentration from about 1860 until near 2000. Okay, so you see the rise, especially over the second half of the 20th century. Of course, now, though, at 2016, we're at 400 parts per million, right? So at least for right now, it looks kind of like we're on the A1FI path, okay? Of course, it's only 2016. So, if I asked you, what's the maximum possible concentration of carbon dioxide in 2100? Based on these 4 emission scenarios, these 6 total emission groups, or 6 emission scenarios, right? Because I have to remember A1 has 3. It's close to 1,000 parts per million. It's about 970 parts per million. And that's A1FI, business as usual, worst case. The best case is that we stabilize CO2 concentrations at 550 parts per million in 2100, and that is what the B1 emission scenario projects, okay? Best case scenario. By the way, A1T is also a really good scenario. Really how it shows technology saves us, and we level off CO2 concentrations at just under 600 parts per million by 2100, okay? So you see a range, okay, in these different emission scenarios, okay? Now, we want to start looking at what the climate models show for the future, but in order to do that, we first have to test the models against observed past climate in order to make sure they are trustworthy. So before you can actually trust the models and what they show for the future, they must be verified. And observed past climate can be used as a test. If a climate model can simulate the past climate, okay, what's actually happened in the past, then there's reasonable chance that the model can accurately predict future climate. So let's see if the climate models can reconstruct past temperature changes, and if they can, then we can have fair confidence that they can accurately predict the future climate. Okay, if the climate model can't simulate what's actually happened, right, then how can we trust it in what it says will happen in the future? So, can we predict changes in past climate?
Okay, can we predict? Can we reconstruct what's actually happened concerning global average temperature, global surface temperature? Well, let's find out. Here are observed global temperature changes versus simulations using a certain climate model, global climate model called the HAD-GEM1. It's a United Kingdom global climate model, assuming only natural forcing factors in green, anthropogenic forcing factors only in blue, and both natural and anthropogenic forcing factors in red. And black, the observations are in black. The gray band indicates the uncertainty of the calculations for all forcing factors. The baseline, 0, horizontal line is the mean average temperature for the entire period. Okay, and plotted are the 10-year moving averages to smooth out the year-to-year variations and get a more look at the net trends. Okay, so let's take a look. Observations are basically this. Okay, so you'll see that the observations are very similar to this figure. Okay, so temperature decreased slightly from 1880 into the early 1900s, 1910. Then it went up for a few decades. It leveled off from the 40s into the 50s and 60s, as we've seen, and then starting in the 70s, it increased and more rapidly than it had been in the earlier part of the 20th century. We've seen that. Okay, that's what we've seen. Now, can the climate models show that? Well, let's first of all run the climate models using only natural forcing factors. Changes in, such as changes in solar radiance, volcanic eruptions. Okay. And what do we see? If we do that, shown in green, well, the models show a temperature increase from 1880 to 1940. They don't show that decrease as much. They don't show much of a decrease into the early part of the 20th century. And then after 1950 or so, temperatures start to level off. Notice that there's no temperature increase during the second half of the 20th century into the early 21st century overall. Right? In fact, from 1950 to close to present, okay, I recognize that the runs end around the end of the 20th century. Temperature has a net slight decrease from 1950 to 2000. Okay, so you do not see this dramatic increase in temperature that we've seen in the second half of the 20th century, right? So then, if you only use natural forcing factors, you can't show that. If you use anthropogenic forcing factors, you can show that. And it turns out that of the three possible ways of running this climate model, using only natural forcing factors, using only anthropogenic forcing factors, or using both natural and anthropogenic forcing factors, the one that matches up most closely with the observations in black is using both natural and anthropogenic forcing factors, shown in red. It shows a decrease at the beginning of the period, and then it shows an increase in the early part of the 20th century. It shows that kind of leveling off and actually a decrease. It lines up, not exactly, but pretty close with the observations, okay? So, what can we conclude from these experiments? One, the models can reasonably predict temperature variations over the past 150 years or so, going back to the late 1800s. And two, most of the observed warming in the past 50 years is attributable to human activities. The reason we know that is because if we only use natural forcing factors to run the climate model, it cannot simulate the dramatic warming in the second half of the later part of the 20th century into the early 21st century. Okay, we need to include anthropogenic forcing factors. So that gives us confidence that humans are the reason that temperatures have increased especially more dramatically in the recent decades. Now, what do climate models show for the future? So now we have evidence to that the models can the models are trustworthy for the future. They can. This was just these conclusions were drawn based on looking at that one climate model reconstructed in the past, but would tell you that that's one, but many. Okay, in general, most of the climate models that are used to predict future climate, in fact, basically all of them can reconstruct past climate. Otherwise, they would not be used to predict future climate. Okay, so the ones that can show that reconstruct past climate fairly well are the ones that are used to predict future climate. So what do the future projections show? Okay, let's look at global temperature increase. Okay, the title of this class is Global Climate Change, but the title of the lower division class, similar to this is MET 112. The lower division one is MET 12. Okay, MET 112 is upper. It's the MET 12 title is Global Warming, and it's a very similar class. Okay, global climate change is more generic than global warming, but global warming is a form of global climate change. And what we often talk about, most often when we talk about climate change, is increases in temperature, which can then lead to other things like increases in sea level, decreasing sea ice extent, possibly stronger hurricanes, what we'll talk about. So how much will sea level go up? Let's look. Here we go. Here are changes in global temperature in the 20th century, the observations and projections of future temperature. How temperature will change in the 21st century according to different emission scenarios. Okay. Now, according to different emission scenarios and also constant concentrations. Let's say we kept global greenhouse gas emissions constant at 2000 levels. Temperature wouldn't really go up too much, okay? But then what happens? And that should be expected, because if concentrations were constant, the greenhouse effect wasn't becoming stronger, then temperatures wouldn't change much, okay? Because, like we talked about, majority of the warming is driven by increasing greenhouse gas concentrations. And so if concentrations remain the same, the greenhouse effect remain the same strength, there wouldn't be much forcing to increase global temperatures, okay? Now, from 0 to 2000 to 2100, we can look at the rise in temperature. The numbers show how temperature is changing from the year 2000. And we can look at, according to A2, A1B, or B1, in this part of the figure. And so we can see, in 2050, right, how much would temperature have gone up by according to one of these three scenarios. But on the right side, right of this part of the figure, I think it's even more helpful, because here you have all 6 of the real scenarios. So you're not just looking at 3, you're looking at all 6, and you're looking at total temperature change from 2000 to 2100, so the 21st century temperature change, and you're looking at the best estimate in color inside of the gray bar, and then the gray bar indicates uncertainty. So let's see if we understand how to read this. Example, B1, best case scenario. Not surprisingly, it was the scenario that had the lowest CO2 concentration at in 2100. Or, not surprisingly, because it was the one that had the lowest CO2 concentration in 2100, it's also the one with the smallest best estimate of global temperature increase over the 21st century. How much? Well, here's 1 Celsius, and here's 2, so 1.2, 1.4, 1.6, 1.8 Celsius. So that is 1.8 Celsius. Now, the range for the for temperature increase, global temperature increase,
from the B1 scenario is anywhere from about 1.0 Celsius to 3.0 Celsius, okay? So recall uncertainty when we're talking about radiative forcing diagram. Well, there's also uncertainty regarding the temperature increase for a certain run. Because remember, like we were talking about, there's multiple runs for each scenario, okay? So, most likely, if the world follows the B1 emission scenario, global temperature will rise 1.8 Celsius from 2000 to 2100, 3.2 Fahrenheit, but it could be anywhere from 1 to 3 Celsius. What's the worst case scenario in terms of global temperature increase? Not surprisingly, it's A1FI, the one that had the highest CO2 concentration. And the best estimate of global temperature increase according to that scenario is 4.0 Celsius, 7.2 Fahrenheit. But it could be as high as 6.6 Celsius, 11.8 Fahrenheit, okay? So let's understand some major conclusions. Okay, here's what I want you to really get out of this figure. The 2000 to 2100 global warming range based on the 6 emission scenarios. Best estimates are between 1.8 and 4.0 Celsius. Or for us Americans, 3.2 and 7.2 degrees Fahrenheit. Okay? So based on the 6 emission scenarios, it's most likely the best estimates are that the world is going to warm up. It's going to keep warming up at between the 21st century warming will be between 3.2 and 7.2 Fahrenheit. Okay. The likely range, though, the total range, it's very likely that the actual range will be somewhere in here, is anywhere between 1.0 and 6.6 Celsius, or 1.8 and 11.8 Fahrenheit. Okay. So the best estimates are 3.2 to 7.2 Fahrenheit, but it could be anywhere from 1.8 to 11.8 Fahrenheit. It's very, very unlikely that temperature it would go up less than 1.8 Fahrenheit or more than 11.8 Fahrenheit during the 21st century. For some perspective on these temperature increases, remember, global average surface temperature went up 0.97 Celsius, 1.75 Fahrenheit from 1915 to 2015. So based on the best estimates, we're talking about an almost double the if we just look at the best estimates, okay, the most likely range, we are talking about a near best case scenario, a nearly doubling what the warming was in this 100-year period for 2000 and 2100, okay? Possibly 4 times as much, okay? So just recognize that temperature is going to keep going up, and best estimates are at a significantly faster rate than what it did during this 100-year period. And it tends to be likelier that the actual global temperature increase will be at the higher end of this range. Because, at least for now, it's more likely that the world would follow, say, an A2 or an A1F scenario than a B1 scenario. Okay? So it's likelier that we'd be at the higher end of this range than the lower end of this range. Not saying that we can't get to here, okay? Or even possibly lower, right? And another thing to keep in mind is that there's a magic number for the 21st century warming that you will hear about. That kind of represents a threshold in how our planet evolves. 2.0 Celsius. That's what the world is. The climate scientists really want to try to encourage the world to 21st century warming under 2 Celsius or 3.6 Fahrenheit, okay? That's just at the lower end of this range here. Because if the warming of the 21st century is more than that, it gets more dramatic for species survival, so when you're talking about extinction of species, you're talking about endangerment, migration. Say a 2.5 the difference between a 2.0 and a 2.5 Celsius rise is a lot more than the difference between a 1.5 and a 2.0 Celsius rise. If that kind of gives you some sense about how 2.0 is Celsius is a critical boundary for temperature increase over the 21st century. Now, like I was telling you earlier, the global climate models are not just used to look at numbers for temperature increase for the whole world. We can look at how temperature increase will vary over the entire planet. So let's do that. And then we can make some conclusions based on this. So, here are projected changes in temperature across the world, surface temperature across the world, according to the A2 scenario. And this starts from basically the average temperatures of the 30-year period between 1961 and 1990. So you start with the average temperatures in that 30-year period, and then you see how temperatures will change by the 2020s, and how temperatures will change between this 1961 through 1990 period and the 2090s. Okay? What do you see? Well, first of all, as you go further into the 21st century, temperature goes up more. There's a bigger increase because you're talking about a longer time period, right? You're going further and further into the future, and so temperature will have gone up more, right? And so then you can start, though, looking at how much, and you can look at for patterns. So already from 1961 through 1990 period, already by the 2020s, some parts of the world will have already increased 2, even 3 Celsius, according to the A2 scenario. And you see that temperature increases more in the northern polar regions, okay? And you see for some regions, such as some parts of the oceans, it takes more energy to heat up the ocean, by the way. Some parts of the Southern Pacific Ocean, this region here in the northern Pacific, here in the northern Atlantic, temperature might only go up 0.5 or 1 Celsius. Okay, doesn't sound like a whole lot, but that's not over a whole long time period. By the time we get into the 2090s, wow. Now look at your temperature increases. The largest temperature increases are in the northern polar regions, in the Arctic, where temperature increases more than 8 Celsius. Okay, 14, 15 Fahrenheit from 1961 through 1990 to 2090s. Okay, that's an amazing increase. Okay. So you see that the Arctic regions warm more than other parts of the world. Okay, the temperature changes are not uniformly distributed. You also see that temperature tends to increase at a given latitude, okay, just at angle north or south of the equator, which divides the northern and southern hemisphere. Temperature tends to increase more over land and ocean, right? So if you're at a particular latitude and you're traveling along west or east, say if you start over North America, you go over the oceans, you see the lighter shading of orange or red, so temperature increases less. Generally, land surface temperatures increase more than sea surface temperatures, and this makes sense because it takes more energy to heat up water than land. Notice, for no regions of the world does temperature decrease between this period and the 2090s. Okay. Here, just south of Greenland over the northern Atlantic, temperature increases 1 to 1.5 Celsius. It's, yes, there, we're studying why that region, it's less than any other part of the world, but it's still an increase. Okay. For Northern California, okay, we could you can zoom in, but on 2, when you look at these climate model runs, perhaps a 4 or 5 Celsius rise, okay, 7, 8, 9 Fahrenheit rise in temperature, okay, from 1961 through 1990 by the 2090s. That's a large increase, okay. That's going to have large impacts when we talk about stronger heat waves, we talk about more record highs, okay, we talk about warmer nights, okay. So, here are some conclusions from that figure. Future changes in surface temperature are not uniformly distributed around the globe. Land surface temperatures are expected to increase more than sea surface temperatures. We know why, because of a higher specific heat of water than land. And the Arctic regions are likely to warm more than other latitudes. And by the way, you might be wondering why. Well, it's being aided, the temperature increase there is being greater temperature increase there than other latitudes is being aided by the ice albedo feedback, okay? That region warms up, the ice melts, the dark ocean, open ocean is exposed, so instead of reflecting 80-90% of incoming sunlight, you're absorbing 80-90% of incoming sunlight. Therefore, the region heats up more, which which starts the series of steps of the ice albedo feedback over again. Okay. Okay, now we're going to talk about other meteorological variables, how they will change in the future, according to climate model projections. How about precipitation? Here are projections of 21 global climate models about changes over the present century in precipitation. And we're actually dividing up the year. We're looking at changes in precipitation in the months of December, January, and February, the winter, generally the meteorological winter in the northern hemisphere, and June, July, August on the right, generally the meteorological summer in the northern hemisphere. Okay, and so we're seeing how does precipitation change for parts of the world in these different seasons, and how much? Okay, how much? All right, so what do you see? Well, look, first of all, some of the largest precipitation changes you see are over the polar regions. Alaska, northern Canada, Greenland, much of Russia. You see precipitation increases of more than 20% in the winter months there. Okay, so more wintertime precipitation in the far northern polar regions. Okay. Actually much of Russia, even much of Western Europe, some parts of northern Europe, northern Canada, all of Alaska, Arctic water region. And part of the reason for that, by the way, is because of that warming, the large warming in the Arctic region, in the northern polar regions. So actually, in the far northern Arctic, it's too cold to snow. It's very dry in the far northern Arctic because it's so cold up there that the air can't hold much water vapor. So like, for example, in northern Alaska gets a few inches of snow a year, okay? North Pole gets almost no precipitation. It's very dry because it's so cold. But what's happening is it's warming up. So especially in how in the winter months it's coldest, in the summer months it's warmer, but in the winter months now it's warming up enough so where you can actually have precipitation, okay, because the air can hold more water vapor. Now you can actually have more snow, and so precipitation's increasing. Precipitation's also increasing over Antarctica, more so in their winter. Remember, their winter is in June, July, August. Their meteorological winter is as it warms up more. So that's interesting. You also see increases in precipitation over the equatorial regions overall, for both, perhaps more so in December, January, February, but you also see it in June, July, August. You see in the mid-latitudes, in some parts of the mid-latitudes, off Baja
Northwest U.S., Mediterranean Sea, Southern Europe, okay, Southern Africa, parts of Australia, off the coast of Chile. You see decreases in precipitation. Okay, so drier in the mid latitudes overall is actually the general trend. So this is using the A1B scenario, and these are averages based on 21 global climate model runs. Okay, going to tell you now, an individual climate model will differ from one another. They differ from one another in the exact changes. So maybe one climate model shows drier in San Jose, maybe another one shows slightly wetter. But these precipitation changes on this slide are based on an average of 21 global climate models. Okay. So here are the net trends for changes in precipitation based on global climate models. The polar and equatorial regions, the high and low latitudes, are likely to become wetter, okay, overall, while the middle latitude regions will become drier. This includes San Jose. This includes Northern California, okay? Overall, precipitation should increase, though. Generally, the consensus among global climate model runs is that overall there's going to be more total precipitation in 2100 than in 2000. And this is partly because warmer air can hold more water vapor, right? And we talked about the water vapor feedback, we talked about the cloud feedback. And with more warmer air, you can have more clouds and precipitation. So yeah, global warming will promote greater evaporation of water from Earth's surface. What goes up must come down. Therefore, global precipitation should increase on average. And by the way, we talk about the mid-latitudes, however, becoming drier. This especially includes areas that are already deserts. Higher temperatures and lower precipitation at mid-latitudes will decrease the snowpack in many mountain regions. Okay. In California, do you know what percentage of our consumable water comes from the Sierra Nevada snowmelt? It's about 60%. Okay, so 60% of California's usable water generally comes from the Sierra Nevada snowmelt. We're very dependent on the snowpack melting for fresh water supply, and the Sierra Nevada mountains in California may receive from anywhere from 30 to 90% less snow by the year 2100 compared to 2000, according to Heiho et al. 2004. This is in your book. So think about that. 2100, the Sierra Nevada snowfall might only be a tenth of what it is in just recently. And just imagine the consequences for us on our state water supply, right? So that's you see there's a very important footprint, if you will, on global warming on California's water supply, okay? Only about 1/3 of ski resorts currently open in Europe will have reliable snow by 2100, according to Agrawala 2007. And even in areas where precipitation does not significantly change, the amount of water available to living organisms, lakes, and rivers will decrease because at higher temperatures, more water will be lost to evaporation. Okay? You might be wondering why the mid-latitudes will become drier. There's evidence that the jet stream, which is driven by differences in temperature between the polar regions and the equatorial regions, will actually shift north. It could weaken, leading to slower moving storms, but there's evidence that it may shift to the north, which is part of the reason that mid-latitudes will become drier. And when we talk about California and water supply, we of course should talk about the drought that's been going on for years now. The U.S. drought monitor is released each week, and this is released for different sections of the U.S., including California. So actually, every week California has its state drought situation updated. And by the way, UNL stands for University of Nebraska Lincoln. That's puts out the drought monitor. And we can look at different categories of drought in California. So this is the most, as of this lecture recording, this is the most recent update for the California's drought situation. So this was released Thursday, July 28th, and it's valid for Tuesday, July 26th. Now, the thing is, there's 5 categories of drought, according to the when you look at the drought monitor. There's abnormally dry, D0, shown by the yellow shading. Okay, we see that in far north, western California. We see that actually along basically the entire coast, from Salinas northward, in fact. Okay, so that's actually good news. The coast is just abnormally dry. In a way, that's good news. Moderate drought is shown by this light brown shading. We see that for some of the Central Valley, far northeastern California. Okay. Actually, San Jose might be in the moderate drought category, it looks like. Severe drought is shown by this orange shading. Southern Sacramento Valley, northern Sierra Nevada, okay, parts of the desert in Southern California, inland East Bay, okay. Red is extreme drought, D3. Northern and some parts of the Central San Joaquin Valley, Central Sierra Nevada, okay, far inland East Bay. And the D4 category is exceptional drought, okay, historic drought. And we see that for far southern San Joaquin Valley, the southern Sierra Nevada, parts of it. And unfortunately, in this region of the southern California coast, where so many people live, right, in the LA metro area. And so then you can look at percentages. So currently, a fifth of the state is in exceptional drought. 43% of the state is in either the worst 2 of 5 categories, extreme or exceptional drought. 59% of the state is in severe, extreme, or exceptional drought. And unfortunately, the entire state, 100% of California, is in some type of drought, okay? Abnormally dry is kind of light drought, if you will. It's drier than normal, okay? And as you may recall, during last fall and winter, and we went through the winter, there's a lot of talk about El Nino helping save California, bringing much-needed rainfall to our state after years of drought and below normal rainfall. Unfortunately, even though the El Nino event was one of the strongest on record, rivaling the 96-97 El Nino and the 97-98 El Nino and the 82-83 El Nino, much of the Bay Area got slightly below, somewhat below, or just slightly above normal rainfall, okay? There was talk that it could lead to perhaps twice as much rainfall as normal. That had been what had been seen for some of the Bay Area cities in those 2 El Ninos that rivaled it in strength and intensity. But, for example, San Francisco Airport, downtown San Francisco, Oakland are actually at slightly less for San Francisco Airport, somewhat less than what they should be at in terms of rainfall since October 1st of last year. Livermore Airport's at a little above where it should be, but the El Nino didn't deliver, well above normal rainfall that was talked about helping end the drought. And if we compare this to last year, there has been some improvement, though.
for example, a year ago, over 2/3 of the state was in the worst category of drought. That has decreased to less than half. Okay, a year ago, nearly half of the state was in an exceptional drought. That has decreased to slightly over a fifth. So actually, the intensity of drought in California has decreased overall. And that's good news. So actually, even though El Nino didn't necessarily lead to well above normal rainfall in the winter and into the spring in some of the Bay Area cities, it did lead to above normal rainfall in some parts of California. And so overall, we have actually had a significant improvement compared to a year ago, which is good news. Okay. And El Nino has played a role in this. Okay. Even though some of the Bay Area cities didn't get a whole lot of rainfall, it was, for some places, more than what was statistically normal, and significantly more than what they had been seeing, right? You might remember that for a few years, as we went through 2012, 13, 14, we were getting well below historically dry years. And just to have, the rainfall of average, even slightly just below or slightly above average rainfall compared to what we were having, also helped for the drought. So, let's talk about some more variables that we can predict using global climate models. We could talk about September Arctic sea ice extent as well as sea level rise. So here's figure 4.35 from the book. And on the left, so first of all, just focus on the left. That's dealing with sea ice extent. So, in red you have observations. Remember, the observations of Arctic sea ice extent in September began in 1979. Back then it was around 8 million square kilometers. And blue and green are climate models projections going to the future. Blue, and they're two different climate models. One is the NCAR CCSM3 in Colorado. The other is the United Kingdom, and obviously United Kingdom Meteorological Office had GEM1. And one thing to note is that the observations show September Arctic sea ice extent declining faster than was being projected by the climate models. Okay? So by the time we were getting into the early 2000s, you see here, sea ice extent dropping down to around below 6, near 5 million square kilometers. And this data ends several years ago. This was before the 2012 record low minimum. This was before September or 2012 Arctic sea ice extent was down here, 3.6 million square kilometers, okay? 2012 would be around 3.6 million square kilometers around here. So anyway, what's happening is that the observations have shown September Arctic sea ice extent is decreasing faster than these two climate model projections had forecast. And these two climate models projections are run in the mid-2000s, okay? This book is published in 2010. It is a bit older now, but this has continued to be a theme. Observations showing faster melting of sea ice in the Arctic in September than the climate models were projecting. So the climate models show September Arctic sea ice extent dropping down to around 1 million square kilometer in 2050, according to the NCAR CCSM3 model, in about 2070, according to the UKMO HADGEM1 model. And then you notice once there's down to less than 1 million square kilometers of ice in the Arctic in September, the rate of melting decreases because it's hard to completely melt the ice, it turns out. But once you get down to 1 million square kilometers, that's so little ice compared to what had been seen, right? So okay, now, and they definitely show, though, in the within later in the 21st century, the two climate models show basically ice-free Arctic summers, right? There's a reason we've been talking about that. Now on the right we have sea level rise. Okay, we have sea level rise based on different emission scenarios. On the left, when you were looking at sea ice extent decrease, those were basically averages based on all the scenarios. Okay, all the scenarios. On right, on the other hand, we have sea level change based on different scenarios. Based on different scenarios from climate models. And so the colored lines are the best estimates for the individual scenarios, and the gray represents the total possible uncertainty, the total possible range. So, 0 meter sea level change is basically applies to year 2000, or just before 2000. So we're basically looking at how sea level is going to change in the 21st century relative to the year 2000, okay? And so you see sea level increase, and then notice how sea level is increasing at a faster rate than it increased in the 20th century. This is what I was telling you about, right? Sea level rose, on average for the world, it rose about 7.87 inches in the 20th century, but it's going to go up more in the 21st century. The rate of increase is more. And the worst case is that by 2100, sea level will be at the top of the gray bar here, 1.25 meters or 4 feet higher. 4.1 feet higher than in 2000. The best case is that sea level rise will be 0.55 meters higher, or 1.8 feet higher than in 2000. That's what I was telling you earlier. Remember how I told you that the climate model projections were showing a 2 to 4 feet rise in sea level in the 21st century? But that's old data. These are runs from several years ago. The newer runs and the newer consensus among climate models, based on faster melting of West Antarctica ice sheet along with other regions, are now showing a 3 to 6 foot sea level rise according to these different emission scenarios. Okay. And if you just focus on the best estimate for the B1 scenario, you see for these runs from several years ago about a 0.70 meter or 2.3 foot rise, and while the A1FI worst case scenario shows about a 1.0 meter or 3.3 feet rise in sea level. Okay. So why will sea level go up? The two reasons we mentioned earlier: thermal expansion, and the more important reason, melting of continental ice along with snow. Sea level is predicted to rise as higher temperatures expand the volume of ocean waters and melt the snow and ice situated on land masses, particularly Greenland, and Antarctica. Okay, and now talking about the left part of that previous figure, showing sea ice extent decline. We know that warmer temperatures lead to sea ice melt, and this process of the ice melting is accelerated by the ice albedo feedback. Two climate model projections from about 2007, nearly 10 years ago, show ice-free Arctic summers by 2050 and 2070. That's what you saw on that figure, right? But recent trends suggest that it could be sooner. If the net trend from 1979 through 2015 continues, it will be about in 2046 when sea ice extent drops below 1.0 million square kilometers. Okay? But because of faster melting in recent years, it could be sooner, 2040, 2035. We're not sure exactly when, okay? But it will happen in the near future. Okay, let's go over a few more projections that climate models
show. Climate models can also be used to help predict hurricane intensity or how hurricane intensity will be affected by global warming. Well, as ocean temperatures increase, there will be more energy for hurricanes, right? Where do hurricanes get their energy from? Warm ocean waters. Why don't hurricanes occur in California? The ocean's too cold. By the way, you might be interested to know there's evidence of one hurricane making landfall in California in recorded history. Not to say only one hurricane has ever made landfall in California, but in recorded history, there's only one known hurricane making landfall in California. And that was the San Diego hurricane of 1858. Okay, the 1858 hurricane, Category 1 hurricane that made landfall in San Diego, very rare, only known hurricane to make landfall in California. Okay. Anyway, as there's more energy for hurricanes, the intensity is expected to increase, and climate model projections show stronger hurricanes overall in the future. And there's consensus among the experts about hurricanes and the connection between a changing climate and hurricanes. But there are uncertainties as to how global warming will affect the frequency of hurricanes. So even though we'd expect stronger hurricanes on average, we're not necessarily saying there will be more hurricanes. But there is strong evidence that of the hurricanes that do form, a greater percentage of them will say be major hurricanes, right? And by the way, hurricane is the name for a tropical cyclone in North America, and in the northern Atlantic and west, north central Pacific waters. But in Australia, they call them cyclones. In much of Asia, they call these tropical cyclones typhoons. Same basic storm, different name though. Same type of storm. How about forest fires? Okay. Wildfires are more likely to occur in hot, dry weather. Okay. Hot, dry weather is represents good atmospheric conditions for fires to occur. If it's moist, that suppresses fire development, and also cool weather can help suppress the fire development. And also sometimes when the conditions are hot and dry, not only that can help form the fires, those conditions themselves, but sometimes in, say, Southern California, these hot, dry conditions can be promoted by Santa Ana winds, you may have heard of. Or in the Bay Area, we call them Diablo winds. The Diablo or Santa Ana winds, depending on if you're in Northern California or Southern California, help promote hot, dry weather. They're hot, dry winds. And also, if it's windy, that can help make the fires harder to contain, right? In the mid-latitudes, forest fire frequency is expected to increase. So in fact, we do expect more fires in the mid-latitudes in the future due to global warming. Okay. Finally, so we've covered what global climate models are. We've covered how they can be used to verify causes of global warming. We've used them to determine how much global warming we'll see in the 21st century. We've used them to look at how other variables like precipitation, sea level, Arctic sea ice extent will change, the possible ranges in those changes. And to wrap this lecture up, let's take a look at how we can use climate models to help determine what we need to do in terms of emissions to help stabilize concentrations of carbon dioxide. Okay, so here it's a figure. Impact of stabilizing, with the British spelling, emissions versus stabilizing concentrations of CO2. We have CO2 emissions, gigatons of carbon per year, on the left. In the middle, we have CO2 concentration in parts per million. And on the right, we have temperature change in degrees Celsius. from the year 2000. And all three of these figures show changes from the year 2000 all the way to the year 2300, almost 300 years in the future from now. And what we have here is basically two different emission scenarios, if you will. Two different emission paths, and the corresponding changes in concentration of CO2 and temperature change according to each emission path. So first of all, we have the emission path in red, constant CO2 emissions at 2000 level. We basically the global emissions of the world do not change going forward for 300 years. And that's, in a way, you might think, well, that sounds good, because you know how global CO2 emissions had been increasing, right? They've been increasing dramatically. So now let's stop them from increasing, and we level them off. We stabilize emissions. They don't increase anymore. Well, what would happen to CO2 concentration if we did that? It would keep going up. It would reach about 500 parts per million by 2100, and it would continue going up into the future. And therefore, because the CO2 concentration goes up linearly, temperatures would also increase over time, close to linear as well. You understand that it's not enough to stabilize emissions. Even if we keep emissions constant, carbon dioxide emissions constant, concentrations go up and temperatures continue to rise for the world. And the reason is because current emissions, or at least 2000 level emissions of CO2, exceed the sinks. More CO2 is being put into the atmosphere than removed, okay? So if you're adding more CO2 to the atmosphere than you're taking out, then that's why, over time, concentrations, the amount of CO2 continues to go up. What you have to do if you want to reduce concentrations, you have to get the emissions down to below, to a point where now you're actually removing more from the atmosphere overall each year than you're putting in, and then you actually start to see concentrations go down. So we have another emissions path that's used to stabilize CO2 concentration at 550 parts per million. Typo here, should be a C in front of the O. So here's this emissions path. In the near future, CO2 emissions rise slightly. They reach near 11 gigatons of carbon per year by mid-century, and then they rapidly decrease. Okay? They rapidly decrease. By 2100, they're actually down to 5 gigatons of carbon per year. And that's about, now we're at about 10. 2016, we're at about 10. So they're down to 5. They go from 10 gigatons of carbon per year emissions of carbon dioxide due in 2016 to 5 gigatons of carbon per year in 2100, with further decreases afterward. If that's done, then the atmospheric carbon dioxide concentrations level off. They stabilize after 2100. They don't increase anymore. They stabilize at 550 parts per million. Hey, that's the best case scenario. Remember the B1 concentrations? And if we do that, we can limit the 21st century warming to about 1.5 Celsius or even less. But yeah. So key conclusions are that stabilizing emissions is not enough to reduce the radiative forcing. It's not enough to stop concentrations from rising. It's not enough to level off temperature increase. Based on above, how much will emissions have to decline in percentage to stabilize CO2 levels at 550 parts per million? The answer is 50%. We have to cut current CO2 emissions at 10 gigatons of carbon per year in half by 2100. 50% reduction by 2100, with even decreases afterward if we want to stabilize CO2 concentrations at 550 parts per million, and that's the best case scenario. And you might remember from later part of lecture 9 on energy and emissions when we actually mentioned this briefly. In order to stabilize CO2 concentrations at 550 parts per million, emissions have to be cut in half by then. So that finishes Lecture 10 on global climate models and the future.